And I want to move on to fields of experts, abbreviated as FOE, as an important class of higher order continuous valued MRFs. Let me give a few motivations for field of experts. When talking about continuous valued MRFs, we spent all of last week talking about Gaussian or Gaussian conditional random fields. However, these are limited in important ways. You can say that these models have limited expressivity of Gaussian conditional or not random fields. The good thing about Gaussian random fields or Gaussian conditional random fields is that you need only specify pairwise interactions. And these interactions by construction are usually designed in a sparse fashion. So random variables talk to only a small subset of all others. Well, the bad thing about Gaussian conditional random fields is that you can only specify pairwise interactions. So something like, I showed earlier with the factor graphs, that you want the contribution of x1 times x2 times x3. You simply could not encode using, or at least not directly, using a Gaussian conditional random field. So as a reminder, in a Gaussian random field, we have an energy that is quadratic in X, where Q is a typically sparse precision matrix. And if I write it out, so let Qij be the ijth element of matrix Q. So in other words, I could write this as a potential psi ij depending on xi and xj. But I can only create pairwise interactions in this fashion. So I could have high connectedness if I wanted. Let me again show in terms of a factor graph. So the 4 neighborhood, if I only introduce interactions between each pixel and its 4 closest neighbors, this is what the factor graph looks like. I'm only showing factors associated with the central pixel here. And if you wanted, you could include factors also with your closest diagonal neighbors. So in black, the black factors alone would be the 4 neighborhood, and the black and the red factors taken together would be the 8 neighborhood, because then I have 8 factors. But this is not the same as higher order. So this is high connectedness, which is not the same as higher order. So higher order factor, for example, would be 1. Let me show it over there. Higher order factor would be 1. Where I have a single factor. Let's say this single factor here belongs to the central pixel. But it also depends on the values of all other hidden states around. So this would be a higher order, whereas the red thing here, that would be highly connected. And of course, you can go beyond 8 neighbors. You can choose as many as you like. But fundamentally, all of these factors here are connected to only 2 random variables in this bipartite graph, whereas here a single factor, in the higher order case, single factor can be related to multiple random variables. So take the example that I gave before. It is simply not possible to write this as a function of x1 times x2 plus a function of x1 times x3 and so on. It's not possible to write it as in general, to express that as a sum of pairwise terms. Okay? If it produces better results depends on the problem that you're trying to solve. So if the answer, or if the problem that you have, necessarily requires interactions between many parts of or if it follows only, well, it depends on the application, and there are some where you truly do need higher order factors. Was there another question or objection? Yes, if you introduce exponentially many helper variables, then this is another way to write yes, you can do that. So you can express any higher order factor in terms of a graph that only has pairwise interactions. It's a very good point you made. So let's say for this specific example here, I could modify it as follows. I could introduce a new auxiliary random variable and connect this new auxiliary random variable to another artificial one with an observation in it. And this is now no longer a factor graph. This is a normal graph. And this I could now turn again into a factor graph by introducing these pairwise factors. So in the picture down here, it would mean that I would have to, for example, for each possible state that x3 can take, I would have to introduce a new interaction between 1 and 2. But since x3 can take infinitely many states, I would need infinitely many auxiliary variables here. But the construction that I showed here works fine for discrete Markov random fields. So I was talking about motivations to go beyond Gaussian conditional random fields when we want to model MRFs that are continuous valued. I now want to give another motivation, an empirical fact of life. Normally it's your parents telling you empirical facts of life. Now you come here and you hear them in addition. So empirical fact of life is that natural image statistics follow a heavy-tailed distribution. So what we can conveniently model with a Gaussian conditional random field is the following. I can consider xi minus xj and use a parabolic potential. In the formula above here, you see, you don't see, well, maybe you see the parabola. So I can always complete the square here and turn it into something that is quadratic in a difference between random variables. So this is in the log space, or this is where I talk about the energy contribution, the contribution to the energy of here a pairwise potential between I and j. And I can take e to the minus the energy of this, which gives me one factor in the joint probability. So if I have a parabola in the exponent, this is something that looks like this. However, if you now look at, and here's an example from a recent paper by Krishnan and Fergus, and this finding has been around for a longer time. If you take a natural image, you know, as natural as downtown, what is it, New York is, if you take a natural image and if you consider the distribution of gradients that you find, so if I make a histogram of values xi minus xj, and if I take the logarithm of this histogram, then you get the blue curve. And if you try and fit this with a Gaussian, so if you try and use parabolic potentials, then the best fit you can obtain to this histogram is, you know, the curve that you see here, not a very good fit. And then you see here a red and a green curve. Those are various better fits. And I want to talk for a moment about what heavy-tailed distributions there are. Well, actually, it's time for the break. So after the break, I will talk about ways to model heavy-tailed distributions and say in general what a heavy-tailed distribution is, and then how to include these in a higher order random field model. All right, so here's the parabola, and there's the Gaussian. And, well, here is the parabola, and there's the Gaussian. And this is, a distribution with infinite range, but it's considered neither particularly heavy nor light-tailed. So Gaussian is, the normal distribution. So as an aside here, short discussion of heavy-tailed distributions. And the Gaussian is considered normal. It's proportional to that. Now, one important model for a heavy-tailed distribution is the student t, which has one more parameter, namely its degrees of freedom. And for 1 degree of freedom, this is proportional to 1 over 1 plus x squared. And that is also called the Lorentzian distribution or the Cauchy distribution, or Lorentzian curve and Cauchy distribution. And it's shown here in this plot. So the blue curve here is the one with 1 degree of freedom. With 2 degrees of freedom, this is proportional to 1 over 2 plus x squared to the power of 3/2. And more generally, for new degrees of freedom, you have 1 plus x squared over nu divided by minus nu plus 1 divided by 2. And if you let nu go to infinity, then you again get the Gaussian. So you see, and this convergence goes fairly quickly. So the highest curve here is one for 30 degrees of freedom, and visually this is already indistinguishable from a Gaussian. If the authors of the Boost library had plotted the Gaussian here, it would have been almost within the line width of this 30 degrees of freedom. But let's let's look at here the one with just a single degree of freedom. This is what's called highly kurtotic. So high kurtosis means that a distribution has a sharper peak around the center and a fatter or a longer or a heavier tail than the Gaussian. And of course, there are low kurtosis distributions also. So this was student T. Another important case is the generalized Laplacian or hyperlaplacian. Note that this has nothing to do with the graph Laplacian that we discussed last time. It's just that so many things in math are called Laplacian because he was a true genius and also lived in interesting times. So he at some point was made Minister of the Interior, I believe, of Napoleon's first government, and was quickly replaced, I think, within the course of a few weeks when Napoleon no longer needed one of the most prestigious scientists of the country and of the century in his own government. And he was then replaced by Napoleon's brother, supposedly because he was such a bad administrator and his brother was so much better at it. Yeah. Okay, so this is the very same Laplace after whom the graph Laplacian and many other things are named. And the hyperlaplacian is distribution e to the minus some parameter of the power of the absolute value of x to the power of alpha. And typical values for alpha are, so if you want to model natural image statistics, are alpha larger than 1/2 and smaller than 0.8. And note that if you look at the potential of this, so if I take the log of this, then for alpha equals 1, I obtain just the absolute value of x, which is still a convex function. And if I make alpha smaller than 1, then I obtain something which is no longer convex. Okay, now back to this image from Krishnan and Bob Fergus. So this is a log histogram of an approximation to the image gradients in the image on the left-hand side. You see that we have many small gradients because our world is smooth and doesn't look like white noise. And we have few large gradients, which is also why here in the very tails, the histogram starts to become a bit shaky, because here our statistics are no longer as good. We just don't have as many counts of pairs of pixels with such extreme values out there. Then you have a fit of this with a parabola corresponding to Gaussian. This was the turquoise here, a very poor fit. Then a fit with the Laplacian shown in red, and a fit with the hyperlaplacian shown in green. And you see that this comes much closer to modeling natural image statistics. Okay, so here was a short aside about heavy tail distributions. And I now want to come to the field of experts as introduced by Roth and Black. There were various conference paper predecessors, but there's a nice PAMI paper, I think it's PAMI, which summarized this in 2009. Stefan Roth is not working far from here in Darmstadt, and Michael Black is now in Tübingen, also quite close. I will start by simply writing down the energy function. So just for comparison and as a reminder for the Gaussian Markov random field, it's something like this. And now comes one of the formulations of a field of experts, an energy which depends on the hidden states and a set of parameters that need to be learned in practice. And we first have a term that couples to the data. And if we just want to denoise, it would look like this. So the likelihood term, the hidden state at pixel I minus the observed gray value at pixel I to the square. So when I say I equals 1 to n, I mean that we have a set of n pixels in the image. And I have a second index j running from 1 to nrf, which is my abbreviation for number of filters. And these filters are weighted with some parameter. And we have a log of 1 plus, I'm writing this here in a quadratic form, stressing the dependence on parameters of these filters. And we're only looking at the ith pixel here. I'm writing this quadratic form out just to make it look more similar to the kind of expressions that we had last week when talking about Markov random fields. So what is X? This is our vectorized set of hidden states. This is what we want to estimate. Then each F is some filter, here some convolution filter. Written as a matrix. So written as a circulant matrix if the boundary conditions are set accordingly. And actually it makes sense to use periodic boundary conditions. And I will say in a moment what these filters are. So the alpha I could take into the exponent. So if I have alpha log of something, this is log times c to the power of alpha. Need to shift this a bit. And so we have essentially what we write here is log of 1 plus, simplifying a little, is log of 1 plus x squared to the power of alpha. And we had already seen something like this. So 1 plus x squared to some power. This is reminiscent of what we saw here. And this was a student t distribution. So in other words, what we have here is the log of one type of a student t distribution. And because it depends on multiple values of x, so x is a vector, I'm only looking at the ith element of it, but still, since I'm looking at the ith element of the resulting vector, but this is a linear combination of multiple random variables. So I could say that this is one way to define a multivariate student t distribution. While it is natural how you would define a multivariate Gaussian, there is a bit of choice how you would like to define a multivariate student t distribution, and some definitions have more merit than others, but this would conform with one definition of what a multivariate student t distribution should look like. So in that sense, if we take many of these here, we could say that this is a mixture of zero mean, multivariate student t distributions. And of course, such a mixture of student t distributions will give you more flexibility in modeling the precise statistics. So if I'm going back to this image here, these were not student t, but hyperlaplacians. But if I took a mixture, if I took a weighted mixture of several hyperlaplacians, I would manage to approximate even more closely the observed blue statistics here. Yeah, so for example, I would like to have it a little more highly peaked here, and you see there's also some deviation between the blue and the green curve there, and these deviations I could make smaller by taking a weighted mixture of hyperlaplacians with differing parameters. And in this formula here, I'm using a weighted sum of student t distributions, or the logarithm thereof, rather. I can also observe that alpha j does not depend on I, and I can reorder a little my terms. This was the likelihood, and then I can first sum over the contributions arising from my various filters, and then have an inner loop going over all pixels. So n was the number of vertices that we have. So to write differently, I could say that this is the convolution of filter mask small f with my original image, but I'll stick with this matrix notation here. I say this is fj of theta j applied to x, and we're only looking at the ith element of it and squaring. So for a Gaussian Markov random field, we had a parabola, and here we would have something that grows more like, depending on what power we use, but it would be something that grows linearly for large values of x. or large differences between values of x. A word about these filters. They can be taken as a linear combination of basis filters. So I'd have a summation over k going from 1 to nrb, which I write for number of basis filters. And for the jth filter, I have a total of nrb coefficients if I want to construct this from a basis of filters. So those would be my basis filters, also convolution filters. And they could be, for example, the filters from the discrete cosine transform. Omitting those, or omitting the one which has a non-zero DC term. Again, these having, only those with a zero DC term. We had seen last time that it is helpful to model long-range correlations if you use that sort of filter. So what do we have overall? We have whatever. So by the way, there are several choices, and this mixture of multivariate student T is just one choice. I'll give you another one in a few minutes. But stepping back a little, what we have is, for a Gaussian Markov random field, we use a parabola. And for a field of experts, we use some kind of robust potential. If I'm plotting this here, for example, as a function of xi minus xj. And one extreme case for a robust potential that I could use would be a truncated parabola. So I could say it's a parabola here, and then beyond some chosen threshold, it simply takes a constant value. And this kind of model, which is not used here because its derivatives are not very helpful if you try to find an optimum, corresponds to so-called line processes that were studied in the 90s, or maybe even late 80s. So in such a line process, you could say, I either decide that somewhere in the image there is a transition, and for switching on such a transition or such a line between two segments, I had to pay a fixed price. This is the price that I would have to pay. Or I can switch the line off, in which case I have to pay a parabolic penalty. And if you now want to find the minimum solution, it amounts to finding a minimum under this problem here, where differences between labels are given by a truncated parabola. Okay, the two problems are equivalent. And this will perhaps also remind you of the kind of things we were looking at when talking about bilateral filters. So with fields of experts, we no longer impose a quadratic penalty on, for example, the differences between the hidden states at neighboring labels or at neighboring positions, but something that grows more slowly, like this. Now, this has some advantage because in analogy with the line processes, it helps us reduce overfitting, oversmoothing. So it reduces oversmoothing, which is good, but it also gives us a non-convex problem, which is bad. So the optimization becomes a lot harder. Also, if you look at this formula here, so we saw that there was a huge jump in quality of the results when you moved from Gaussian random field to Gaussian conditional random fields. So when you made the potentials depend on the observations. And here in all of this smoothness prior, you don't see the observations anywhere. So in other words, this is not a conditional random field. And I think making it conditional is a good topic for future research. It's less necessary than for Gaussian conditional random fields because this conditioning in the Gaussian conditional random fields helped us fight over smoothing. And here we already have less over smoothing because of these robust potentials. But even so, I could imagine that conditioning on the observations may further improve results. I want to give a further formulation using a different set of potentials here. This is the one used by Schmidt from the Road group in 2010. Paper starting with generative something, I think a generative analysis. Not quite sure how the title goes on. Or also from the Road group, there is a paper where the first author is Gao. It's from DHM 2012. And they look at Gaussian scale mixtures. With Gaussian scale mixtures, you can also approximate any robust potential that you want. And I have some slides here from Harvard Ruhr, which shows or which summarizes what is known about the relation between the Gaussian and various heavy tail distributions. Namely, if you have random variables z and v, and z is a Gaussian, then you can create a new variable, x, given by z divided by v. And now, of course, various choices of v will give you different distributions for x. And if you use Gaussians with distribution over these precision parameters, then if this distribution is again Gaussian, you obtain a student t distribution. If it is Kolmogorov-Smirnov distributed, you obtain a logistic distribution. If it's exponential distributed, you obtain the Laplace distribution. So this shows that this is not just a matter of fitting, but really there is a deep connection between the normal distribution and these heavy-tailed distributions. However, you can also just look at it empirically. I have a picture here from an important paper by Gieman and Reynolds, you see in 1992, where they show how a robust potential can be locally approximated by parabolas. And similarly, you can express heavy-tailed distributions as a mixture of Gaussian distributions, which is the formulation that we will use here following Schmidt and Gau. So for a Gaussian scale mixture, the energy again depends on the hidden state x. And then on the weighting parameters alpha that we already just saw. And it also depends on the set of filters. And it depends on the observations, at least in the likelihood term. And the observations are given, but these are the parameters to be learned when you want to solve a concrete problem. Again, the first term here corresponds to a Gaussian likelihood. Now we have a summation over all pixels and a summation over all filters. And now comes the mixture of Gaussians. I'm writing NRS for number of scales, because each Gaussian has a different scale. Those are the weighting coefficients. So the J filter is constructed out of weighted sum, weighted by alpha jk of different Gaussians, which come now. Now I can read my own handwriting. This was meant to be a sigma here. I omitted the observations. And then again, we have responses to various filters. Here only for the ith pixel. And then as a technical aside, there is an extra regularization term, because here if you take Fj transpose and Fj together, this gives you the precision matrix Q. And we had seen that it's good to use ranked efficient Qs if you want to model long-range interactions. But we saw in the discussion of intrinsic Markov random field processes that if you have a ranked efficient Q, then you would, for example, assign the same energy or the same probability to any realization regardless of its shift. So if you add a constant to shift it up or down. And this means that your whole distribution is no longer normalizable. And if you want to be able to normalize it, then you can multiply the thing which is degenerate in some dimensions with a Gaussian, and it's that Gaussian which gives you multiplied with some small number epsilon here, or we already have big epsilon, so let me call, multiply it with a small number delta. This is a regularizer that you can add if you want to have something that can still be normalized. Okay, so unfortunately, the logarithm and the exponential do not cancel because we have a weighted sum of Gaussians here. And by weighing them appropriately, so let's say I'm adding a very narrow Gaussian and wide Gaussian. So if I add these up, then I may obtain, for example, something which has a much higher peak in the middle than a normal Gaussian would. And this can, for example, be made to look like a student t-distribution or a hyperlaplacian or actually anything else if your data suggests anything else. Okay, so it's a very, so essentially everything that is symmetric and monotonically decaying, you can represent by such a mixture of Gaussians. It's one of the, so you're asking how do we get sigma? It's one of the parameters of the procedure. So the parameters are these weights alpha, the standard deviation sigma, and then the nature of the filters themselves. And sigma. Yeah. We're trying to learn alpha and f and sigma, yes. Mm-hmm. Okay, so here was another field of expert. Again, it's not conditioned, the pairwise term or the smoothness term is not conditioned on the observations. And these were two specific formulations, and we can summarize all of these formulations as in the following. So a general formulation in terms of cliques and compatibility functions looks as follows. Probability of the hidden states X and observations O given a particular parameterization is the likelihood of your observations given your hidden states times e to the minus x transpose x with some value delta that is very small. So very small precision or very large standard deviation. This was for the normalizability that I just mentioned. We have the partition function depending on the parameters. And then I continue in the next line. A product over all cliques in the set of edges of my graph. So those would be the cliques. And those would be the hyper edges in my probabilistic graphical model. Then we have a product over various filters or experts. I again write NRF for number of filters. And then we have, so in the log domain or energy domain, I always call these potentials. And here in the probability domain, I call it compatibility functions. which in practice is one amongst a large possible set of heavy-tailed distributions that I could choose from. Where I take a linear combination of the hidden states X that are in the clique C, and the weights for this linear combination, they are just the vectorized point spread function of the convolution filter that I always previously used. So of, excuse me, Fj. And then this depends on lots of parameters. So theta j would be the parameters of the jth expert. So rather than having a multivariate Gaussian, as for the Gaussian Markov random fields, we now have a product of heavy-tailed distributions, each of which is a function of not just one random variable, but of a set of random variables. So for example, we show the following. I'm again showing a small number of random variables. I make the observations in red. And I've used a line width that makes them look like they're almost filled circles, because observations are observed. And now I will show only the factors belonging to the central pixel, or it's going to be completely messy. So let's say the first term here, the likelihood term, I will show in green. So this is a factor that's connecting here the central pixel with its observation. At least if I use here a mere least squares difference, as I did in the two equations shown. But I could actually use something more complicated. So if I wanted to deconvolve at the same time, then I could connect then I could connect my central pixel to more than one of these observations. But here, let's say that I simply look at denoising, and I just take the square difference between the observation and the central pixel here. And this time, to avoid making a complete mess of this picture, I will only show a single of these multivariate or these higher order potentials, namely only the one belonging to the central pixel. So I'm only showing the factors here that belong, let's say, to this central pixel. Again, O are my set of observations here on a tiny grid, and black are, so observations were O, and black were my hidden states. All right, and if I now have a function f that takes a linear combination of all points in this clique here, then I need to draw edges between each of the hidden states and this factor here. So what we have now is a true higher order factor. So if I want to color code, I've shown the green term, and this here would be for one particular clique only, the blue term. And I have not brought pictures of what these filters look like. They are learned, but they typically look like very high frequency things, and typically have or are forced to have a mean of 0. So they look like higher order derivatives, for example. So further up, I show two formulations in the energy domain using different types of robust potentials or heavy-tailed distributions that were combined. And down here, I've now written this in terms of cliques of the probabilistic graphical model. Now, for the mathematically inclined among you, I have good news. When we talked about denoising a few weeks ago, I said that even the most fancy MRF methods, they cannot compete with heuristic ones. And in the meantime, I've heard that that is no longer true. That if you take a model like a field of experts and optimize it very carefully, that you can then obtain, if you learn the parameters very, very carefully, that you can then obtain denoising results which are on a par, not better than, but on a par with the heuristic methods. And here is a very small example. So actually, this is an example from 2009 from this paper of Samuel and Tappen, who were the first to show that it makes a lot of sense to train or to find the parameters, to learn the parameters by minimizing the empirical loss on the training set. Rather than maximizing likelihood. So for maximum likelihood, you need as input clean images. And then you try to learn this image prior P of X so as to give these clean images the greatest possible likelihood. Whereas if you want to minimize the empirical loss, you need as input a training set of both noisy and clean images, which should correspond to each other. So you have a noisy version of an image and then the clean version of that image. And if you will then plug the noisy image into a field of expert, and if you find the best set of hidden states according to your current parameterization, you obtain an estimate, let's call it X star, and then you can compute the loss between, you can then compute the loss between the X star for the current parameterization theta, at time step t that you found, and between the ground truth. So let me call the clean image O. And then you can take derivatives of this to find parameters that will give you a smaller loss. And doing the former, so minimizing empirical loss, is a lot better than maximizing the likelihood. This was the important contribution from this Samuel and Tuppen paper. And LeCun has also made this point very clearly. I have borrowed a couple of slides here from Jan LeCun, who says that you should really train in a loss-based fashion. Okay. Now I want to mention another application where these models perform very well. This is a picture taken from the Roth and Black paper. So one application that we've seen was just denoising. Here another application is in-painting. And you see an example here. On the left is an image on which somebody has typed, and you want to recover the image. And to that end, you mask anything that is red, and then keep as observations everything that is not pure red, and then try to find the most likely values for those hidden or masked pixels. So let's say I index with the script R the set of red pixels, and you now want to in-painting means you want to maximize the probability of the subset given all the remaining pixels. So I write -R for the not red ones, which are simply initialized to be the observations at those locations. So here, denoising is not considered. The image is considered to be noise-free. You just want to get rid of, or you want to fill in the masked pixels. Well, and actually in B, I think that looks pretty nice. And then on the right-hand side, you have an inset. So this would be the image to be filled in. Then in the middle column is some competing method. And in the final column is what field of experts do. And here, for example, you can, or is it the wrong way around? Okay, excuse me. So C was the competitor, and this was here the field of experts. And you can see that the field of experts, for example, does a little bit nicer here in the, so if we believe, we don't know because it's a masked image, but if we believe that the X is actually, continuous here straight, then fields of experts do a little bit better. Because they have learned natural image statistics a little bit better than this competing method. And these in general, these in-painting results are always nice to look at. So it's quite stunning what you can recover. Yeah. Yes. Yeah. So the field of expert is trained on a set of images, and then this is an image that was not previously in the set. Yes. Yeah. You have to. So do you have to take care of what's in the training set? As always, yes. So if you try and make predictions on something that is, completely outside the training set, in this case, in terms of image statistics, then you will do badly. And in general, fields of experts will also do badly in the reconstruction of textured regions, because if you look at the energy function, so in the absence of, so essentially, when you have a highly textured region and you want to fill it in, it will fill it in with something that's too smooth because you have a model that encourages smoothness, or you have a prior that encourages smoothness. Now the problem is non-convex, so optimization in this model is a lot harder than in Gaussian Markov random fields. You can either do something simple like a gradient descent, or you can do something more advanced like half quadratic splitting. And I have a paper here by Champagnat and Idier, who showed that half-quadratic splitting is one particular instance of iteratively reweighted least squares, and for the kind of application here can be considered as an embodiment of the expectation maximization algorithm. Half-quadratic splitting is a technique that goes back to this work of Giemann. So he wrote 2 papers in which he showed how you can approximately solve a non-quadratic problem through a series of quadratic problems. And the idea is to locally approximate your true target function with something that's quadratic. And if you use half-quadratic splitting, you iteratively solve a least squares problem. So you could say that you iteratively solve for the hidden state in our application here of a Gaussian Markov random field, where the Gaussian Markov random field is locally fitted to the non-Gaussian field of experts. So these fields of experts are currently the best thing out there to model truly higher order interactions in continuous valued MRFs. So I'm pointing again to this factor here with the many connections. And it is truly higher order because we can not write or not rewrite this kind of expression, or we can go to one of the more concrete formulas up here. We cannot rewrite this concrete expression as a sum of just pairwise terms. This is why it's truly higher order. Why is it called field of experts? Because Hinton proposed in the early 90s, I believe, a method called product of experts, in which he argued that if you want to model a complicated multimodal distribution, you can write that down as a factor of much simpler distributions. So, for example, this is not exactly what he did, but you could think of, or I could define a simple distribution being one which has parallel contour lines. So let's say I could take a distribution which has 2 Gaussians, regardless of how far I am in this direction. So if I want to draw the corresponding contour lines, excuse my bad painting, but it would look something like this. And I could now multiply this with other simple distributions. So for example, another distribution like that, but here at a different angle. And then the product of these two will already give you non-trivial multimodal distributions. And Hinton argued that, take anything complicated and model it as a product of simpler things. And we have here a product of simpler things. So this is, the product over here, these local filters or compatibility functions or experts, but is used in the spatial context and is hence called field of experts. The expert is a function that tells you in a local context what should have high or low energy or high or low probability. So we have overall a prior for the entire image, but this prior is constructed from a product over cliques only. And these cliques are strongly overlapping. So if I show a different picture here, let's say these are the pixels in my image. Now it depends on what kind of filter I use. If I use a single filter which measures a derivative in a diagonal direction, say, or in an oblique direction, then this would be one clique, and that would be the next clique, and that would be the next clique, and so on. Yeah, so I can fill my entire image with these cliques now. And actually, for each clique, there is not just one expert, but multiple experts. So we have a product here going over the cliques. They're here. But in addition, I have a product going over the different experts. So I have multiple guys having an opinion here, and I'm multiplying all of them to obtain the overall energy or probability for a local set of random variables here. And then, because they are overlapping, I obtain something, or I obtain a non-trivial prior for the entire image. Yes, the each expert has its parameters, and and the experts taken together are made. If you do a maximum likelihood training, then these experts are made so as to give the greatest possible likelihood to the training images that you provided. And the hope is that when you later make predictions, this prior will constrain your solution in a favorable fashion, namely to bring your estimate back to this, to project it back, or to bring it back to this realm of images that look natural according to this model. Okay, thanks.